All right, check 1 2. I think we got the sound working again. All right, nice. Welcome back to another week of OS Dev, Kernel Dev, gardening, as I call it, where I embarrass myself live on the internet. And I have good news. My build works. Last time, my build just didn't work as soon as I tried to start the stream, but we're in progress. Build's working. We have our basic thing here. I haven't really written any code. I've just customized a couple things. I think I mostly changed a bit of the color. No. Yeah, it's been. Oh, there it is. Yeah, I was playing with the different colors for some of the VGA stuff. I am just going to commit this stuff. Yeah, maybe we'll clean that up later or whatever. But nice. I'm going to continue working with these kind of homework things with this MIT class today. Last time we were working on this stuff, and that's kind of where we ended, learning about how the console works. Yeah. I don't want to spend too much time on the console again. I think the topics I'm mostly interested in getting into are like interrupts and virtual memory. So I'm going to focus more on that, I think. Just kind of monitoring the stream, making sure we're good. But I think we should be good this time. Checking my tie. All right. Let's kick it off. So this is where we left off. There's like this code in console.c, and this is actually the code that's responsible for scrolling the screen when basically too much text is written to the frame buffer. Moving on for the following questions. Calling convention stuff. Yeah, I don't know if I really need to go through all this. In the call to printf, what does FMT print? Okay, so FMT is what the first print f dot print. I think it was this one. Or no, a C print f is in here, I think. I should just search for it. C print. All right, this is silly. I can't. Where is? Okay, I'm pretty sure it's here. Yeah, C printf. So so the question is. What does format point to? It's format string. What does AP point to? Oh, so format points to these things. AP is the variadic arguments. List in order each call to cons put C. Yeah, honestly, I don't really care about this. Like, I'm not going to do that. Run the following code. What's the output? H something with a string. It is amazing that things from 2008 are still so relevant for today. Yeah, totally. I mean, I think overall that's definitely true. There's some weird. I guess actually, yeah. I mean, all this stuff is like how processors boot up. But yeah, totally. And I mean, I think understanding history and is always useful. So even though like there's more modern ways of doing things, maybe like like I'm writing code for like an IBM PC or whatever, which is not the most standard hardware. And like last stream, I was working on my display driver, which like it uses like the CGA display protocol, which is super old and legacy, but you can still learn a lot, and especially for someone like me that doesn't really know like a lot about this, which is why I'm doing this. Yeah, super helpful. So yeah, go 2008. Okay, what's happening? Unsigned int big number. What's the output? Explain how this output is arrived out in the step-by-step manner. Okay, and here we're passing an integer pointer as a string. So this is probably some ASCII characters or something, so it's going to print a string. Okay. This output depends on the fact that x86 is a little endian. Oh, you said I2 would be flipped around probably. Okay. Following code. Okay. Okay. I don't care about any of this. Okay. Final exercise. And we will write a useful kernel monitor function that prints a backtrace of the stack. A list of the saved instruction pointer values from the nested call instructions that led to the current point of execution. Oh man, all right. Let's see. Determine where the kernel initializes its stack and exactly where in memory its stack is located. How does the kernel reserve space for its stack? And at which end of this area is the stack pointer initialized to point to? All right, let's see. I think I kind of touched this already, but where's the main? init.c. Right, so no, but it's here. Okay, so yeah, before we even get to C code, we need to set up the stack. We relocate, jump to high memory, clear the frame pointer, nuke the frame pointer, so that once we get into debugging C code, stack backtraces will be terminated properly. Nuke the frame pointer. Right, call. So I'm guessing, yeah. Set the stack pointer. Yeah, more importantly, set the stack pointer. Boot stack top. Yeah, here's where I kind of don't know assembly syntax or whatever. I'm not completely sure what's actually going on here. Daily Run, hello, welcome back. Good to see you. Hope you're doing well. I'm trying to understand exactly what is happening here. So obviously we are assigning something to the stack pointer ESP. I'm trying to figure out what it actually is though. Boot stack space K stack. That's interesting. Actually, this is kind of new to me. Yeah. Boot stack. Oh, I see. Interesting. Okay. I think 2 episodes ago or 2 weeks ago, I was looking into this a lot more deeply. And the question was, what stack is this early kernel entry code running on? Hey, I am new here. I wanted to ask, is it using Apple Silicon? No, this is like, this is running on x86. This is This is like the farthest away thing from a modern operating system. And first of all, yeah, to be clear, I also didn't even really write a lot of this code. I'm actually following this MIT class, which has this very simple minimal OS. And I'm just kind of getting started with kernel development through that. So this is not Apple Silicon. Although if you're asking if my computer is Apple Silicon, yes, it is Apple Silicon. And I'm running, but that hasn't been a problem for me. I'm just using QEMU on Apple Silicon, and it works just fine. Yeah. So the question was, what stack was this early kernel entry code running on? And I think the answer was it's running on the bootloader's stack, because the bootloader was running here and transfers control to the elf entry directly. But otherwise, there's nothing that's going on with the stack here. And so immediately on this, when we jump into the entry point, which is right here, we're going to still be running on this stack frame of the bootloader. And then now here's where we start to set up the stack for the kernel code. And what it actually looks like, as is commented here, is that in the kernel binary, they reserve space like for the stack in the data segment, which is very interesting. I haven't thought about this deeply before, but that's kind of not what I would expect. I would kind of expect that as the kernel, you just pick some location in memory, and like you just use it. Why would you have to allocate it in your binary? Not quite sure. Hey, hello. Is it Fisan? Also, hey, Andika and Roni. Yeah. Welcome to the stream. Glad to have you. I forgot. I want to add like a thing, like a little text thing, like this text thing, to the top left, to adjust kernel. Feel free to say hi. Yeah, I don't really know what exactly we're doing, but yeah, I'm just gonna put JAWS kernel. Feel free to say hi. Okay. Save. Good. So yeah, so it looks like we're literally reserving space in the binary for readelf. Boot stack. So we're reserving like a large chunk of memory in the binary for the stack actually. Global boot stack top. Doing this way, you're sure that no other symbol will be placed inside your stack, rather than if you picked an arbitrary location. Yeah, I mean, yeah, that's a good point. Otherwise, maybe you don't know, what's in memory or something. So, yeah, totally. I can totally see that. Learn something new. Okay, so reserve a big chunk of space. It apparently is 8 page sizes. So 8 times 4K, like 32K or whatever. Oops. Yeah, 32K. Rather back to Python. Rather back to Python. Not quite sure what you mean by that. Are you like going back to Python coding after seeing this or something? Okay. So then yeah. Interesting. Yeah, so I guess I kind of wish I understood how to read this a little bit better. I'm going to copy this into ChatGPT and ask it to explain this to me. Here is a fragment of my assembly file. Can you please explain it? It's just so much more convenient to set up your kernel like so. I guess I would imagine that eventually we're going to transition away from this stack. I mean, it's called boot stack. I feel like that kind of implies that it's not the permanent runtime stack. But I guess, yeah, I guess I will learn more about this. Okay. Data, so data directive, we're operating on the data segment of the binary. Page shift, we align to what? 12, what? Okay, page 2 align. Number of bits to shift. Okay. 12. Right, okay, got it. Global boot stack. So this I guess this is how you make declare like a variable or like a label. I mean, so yeah, I guess a label in the assembly. This is used for data functions that need to be referenced. Is boot stack ever like boot the actual label boot stack is not it's not referenced. It's just it only exists to reserve a bunch of space. Reserves a block of space in memory. K stack size would be something something. Okay. Similar to the global directive. Okay. It's placed immediately after the space reserved for the stack. Okay. Yeah, I'll show you guys. It's okay. It signifies where the stack ends, which is crucial. Okay. Okay, this totally makes sense to me. We have like this big block of memory, and it like goes up in memory for 32K. Like, yeah. And then we can get kind of like a pointer to the end of that, and then initialize our stack to the top of this region, as one does. Cool. I'm just thinking about like how this is represented in the binary, because it would be kind of dumb to like have our binary literally be like 32K in size. Let's see if we can learn something about this. So here's our symbol table. No type. So we get, apparently we also have, yeah, we have these like virtual addresses of the different symbols. This is boot stack top and this is boot stack. And yeah, we can actually see. So hex 1000 is 4K, I believe. Time to go to my basic math, or what? So hex 1000 is 4K. And we can see that boot stack plus hex 8000 gets us to hex A, which is 10, right? Yeah, I'm pretty sure. And then that's our boot stack top. Okay, that checks out to me. So we can see that we've reserved hex 8000 bytes. Interestingly enough, entry page dir is also like right there or something. Boot stack top occupies no space or something. It's just a label. And so I guess the next thing in our data segment, apparently according to our compilation process, is just going to be all these like entry.pagedir global variables that we have. Entry pagedir. No, not this. This is just a forward declaration because it needs to be referenced by the page directory. So it's going to be this thing. Apparently this thing is just next in the, it's just the next global variable we have. So it occupies, it's the next thing, but also boot stack top doesn't occupy space. And so they kind of actually share the same address. So it's interesting that, just to learn a bit more about this layout that's happening here. So for example, if we were to do the opposite of a Stack Overflow. So a Stack Overflow, maybe it's kind of a good time, like to go, so draw some more rectangles. Here's our stack. I always forget how to fill it in. Here's our stack. It's like 32K stack. That this region in the binary, and our stack pointer starts all the way up here, and then like points here. And the interesting thing is then we also have our page tables, and that is immediately contiguous with our stack. And so if we were to have any bugs, for example, that cause us to like start writing up here, we're actually going to corrupt our page directory, which would be very interesting if that happened. The page directory is mostly sparse at this point in the code because we only have 2 page directory entries. And so actually, if we like start corrupting memory in the page directory, probably nothing bad would actually happen. It would, yeah, I think actually nothing bad would happen. It would just maybe accidentally allow different regions of memory to be accessed, which if we then accessed different virtual addresses, it might then cause a crash because the page directory entry is all corrupted and weird. But it's just interesting to know kind of what the memory layout, what's going on. But for the moment, under all correct circumstances, the stack pointer points right to this boundary point and then starts going down from there. And we should just be careful to like never like accidentally like go up too far. Okay. Okay, good. So so now we have achieved total understanding of the stack. And so now we move that pointer into ESP. And from here, we can actually call into the C code. And now would be a good time to probably disassemble. Because I want to kind of just like look at D entry, no, 6 init, right? And how do I make object dump how to Intel syntax? I always forget. You can do it. You can add the -m Intel. i386 init. Good. And the reason why I actually want to read the assembly is just to really fully understand this transition from assembly into C code at like the deepest level. So what we have, we do 2 things and 2 things only. We nuke the frame pointer and then we set the stack pointer and then we call into our C code at this symbol, which is then going to trigger a normal kind of start of a function where we then push the frame pointer, reset the stack pointer, reset the stack pointer, push the frame pointer, reset the frame pointer to the new stack frame, because this code is under the assumption that there's like other stack frames above it, which is actually not the case for us. This is kind of like the first stack frame of the kernel, really, because prior to this we were operating on the bootloader's stack frame, which is somewhere else that I don't know. So yeah, reset the frame pointer to point to the stack pointer, like take ESP, put it into EVP, and then subtract the stack pointer and use it as like the base for different stack operations and whatnot. Apparently we need hex C stack space for this function so far, which I wonder why init.c what because as far as I see, okay, because I didn't really think we had that many, like we're not doing very much in this function, but we are declaring extern char. I guess we are declaring. Interesting. I actually don't really know what this compiles to. Extern char, like usually if you declare a char array in your function, that just takes space on the stack. But I don't really know what happens with an extern char. And my guess is that actually it's storing two pointers, because the data comes from elsewhere. And this is actually these are symbols that come from the linker. Yeah, I actually kind of wonder if we could replace the char star thing with a pointer, which to me would be a little bit more clear. Oh no, I reformatted everything again. I need to disable my format on say. I need to figure that out. That's so. Eventually, I will need to figure that out. Maybe it's not even syntactically possible. Oh wait, okay. The star comes before. So does this work? Does that compile? No, it didn't. What? That did like not. That did not work. So did that actually break? Did I actually really just break things? Just. But that would be kind of a weird. Like it just didn't print anything on the screen. But apparently that was actually important to do it like this. Yeah, I don't know why. But interestingly, it seems like it compiled and then just broke at runtime. So, so yeah, for some reason, it's actually important to declare like these arrays. But anyway, my point was, I think it's just two pointers that are on the stack then, which doesn't really make sense because that would only be 8 bytes and not 12. We can learn more about this by looking at where everywhere ESP is used. Also, wow, it adds, like, it subtracts the stack pointer. And actually modifies it again. So I'm not actually, yeah, maybe that's totally legit. I'm not very used to reading 32-bit x86. So, yeah, it'll take some adjustment. But more importantly, where are these things used? These are only used in the memset call, which is right here. Move EAX. And then just sub. That's kind of weird. Okay. Push EAX. push 0, push another address. Yeah, so the calling convention on 32-bit is using the stack for a lot of things. Subtract from the stack pointer. Yeah, definitely clear to me that they subtract because the stack goes down, but then they're adding to it here, which is a little bit unusual for me. For me, what I'm used to is that usually the stack pointer doesn't change very much during a function. Like, you subtract the stack pointer once for as many local variables as you will use, and then it just kind of stays there for the most part. So I'm surprised to see that it is being modified so much, but maybe you know the answer to that. But also maybe it's a 32-bit thing, and maybe this like phenomenon of the stack pointer staying constant is more of a 64-bit thing, which is why I'm more used to it. But like, it seems, yeah, like after every function call, oh wait, no, okay, that makes total sense. Like, the caller is responsible for repairing the stack, like quote unquote repairing. Not, after you make a function call, like before you make a function call, you do all these extra pushes. So you need to like you need to do the inverse of all those pushes to kind of bring the stack back into its original state. So actually, that does totally make sense, and that also explains why I'm not familiar with it, because on 64-bit, you use registers for almost everything calling wise. And so there's no need to modify the stack like this. So that makes sense. Although these numbers are kind of interesting. So you do 3 pushes, and then what is that? That should be 12 bytes, right? Each of these should be what? 4 bytes. EAX is 4 bytes. 0 is probably 4 bytes, I would imagine. And yeah, we do 2 function calls. Apparently this cons init, okay, it doesn't take any arguments. Interesting that the stack is like not repaired right after memset, but like after cons init for some reason, even though cons init doesn't use any arguments. And then here is what? A local variable for the number 5, which they need to write into the stack. Okay, yeah, it's taking me a minute to get used to 32-bit again. But usually on 64-bit, you would just write the 5 into a register and then call the function. But on 32-bit, you need to be actually touching memory like all the time to do this stuff. Interesting. Yeah, just to simply call a function with 1 argument, you need to literally write to memory to do this. Yeah. Push 0 is a single byte push. Really? Thanks for checking that for me. 6A. Got it. Push immediate. Just to show anybody else how to. So x86. What is it? 6A opcode. Oh, that's lame. All right. x86 push. Okay, here's the Felix's website. 6A push 8 immediate. So you're totally right. Yeah, that's interesting to me because stack is like totally unaligned then. Push EAX. So if I'm reading that correctly, then this pushes 4 bytes, this pushes 1 byte, this pushes 4 bytes. So then the stack is like on is like not aligned. It's like it was subtracted like 9 bytes. And then added 8, added 8, which is still like not aligned, I think. Am I being like dumb or something? Like, does that, I could debug this and step through it, but I didn't, I wasn't really planning on going to this level of depth really with this. Yeah, surely this code works for some reason. Push, printf 5, blah, 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 blah. Anyway, the important point was just looking at the prologue, basically. So it pushes EBP. Basically, the dependencies of this are EBP and ESP, which is exactly what we prepared before calling into the function, because it pushes EBP and then also starts to take advantage of ESP and assumes there is a stack available. But otherwise, that is it. Jump. Okay, nice. All clear to me. So determine where it initializes its stack and exactly where memory is located. Okay, it initializes its stack, well, like right before, in the entry code that we just looked at in the assembly, where it nukes EBP, sets ESP. The memory is in the virtual memory of the kernel binary region. Just curious, how big is the kernel? Man. Ugh. Sorry, man. 94K. I was like, so I wonder. I think actually there's 32K of stack on disk right now. I wonder if that's true. But the kernel binary is like 100K. So it's possible that, yeah. One easy experiment. Thanks for the subscribe. Just heard the sound. Appreciate that. Thanks, DB. One experiment we can try very quickly to actually see if we are consuming space on disk for the binary is to adjust the K stack size. That's a super quick experiment. Let's change this to 4. K stack gap. Interesting. Okay? I don't know what stake. Do not know what. Oh, what is going on? K stack top current base. Okay. Let's change this thing. Make. And take another look. Yeah. Yeah. So does that make sense? I changed it to 4, which means 16K of savings. 78 plus 16. Let me move my calculator thing. 78 plus 16 is 94. So that confirms it. So that confirms that really the kernel, like the 32K of kernel stack is really like in the binary taking space, which is interesting to me because that seems like something we could optimize by storing that in the BSS, for example. In fact, I mean, we literally have init code that goes out of the way to zero out the BSS. Like, why not just put, well, I see. Okay, the kernel, this region doesn't even need to be initialized. And so maybe it would be a little bit inefficient at runtime to have to initialize it with zeros, but it would save binary size for our kernel to store it in the BSS rather than the data segment, where it's just taking up 32K of zeros on disk. So that, okay, so now we have achieved full understanding of that, which is interesting. Okay. Okay. Okay, this is all... okay. Oh, I forgot, I wouldn't have my break timer. I'm just gonna do a 20-second break because I forgot, and it's been 40 minutes already, so I'll be back in 20 seconds. Okay, stretch break is over. Okay, if all the functions, it's possible to trace the stack through a chain of pointers. This capability can be useful when a particular function causes a panic, but you aren't sure who caused it. Stack trace lets you find the offending function. Okay, to become familiar with the C calling conventions on x86, find the address. Examine what happens each time it gets called after the kernel starts. There are two ways you can set this breakpoint. Okay. Test backtrace. What? Yeah, you... Oh, I just caught... Okay, there. Yeah, they put it inside the data. Personally, I have it inside BSS and it works fine. Yeah, cool. Okay. Find the kernel, object kernel.asm, object kernel.as, is that real? Do I have, okay. Test backtrace. Okay, I don't know what's going on. This is totally new to me. So test backtrace is this function that gets called. Oh, I see. This is the thing that produces like this output. Oops. This like entering backtrace 543210 thing. Okay, that's just some code that runs in like the init before the kernel monitor. So the breakpoint there, and examine what happens each time it gets called after the kernel. So is it like recursive or something? So was that up here? Okay, yeah. So yeah, it's this recursive function, and it takes an integer, and if it's greater than 0, it recurses. Otherwise, it doesn't mon backtrace. What is this? Mon. Otherwise it returns 0, okay. Okay. After the kernel starts. How many 32-bit words does each recursing nesting level test backtrace push onto the stack? And what are those words? So I'm pretty familiar with this already. I'm pretty sure, I mean, we were already just looking at some assembly here, but for example, we can just statically, I mean, so my guess is 8, because for every time you call a function, you do a call instruction which pushes the PC, and then the first instruction of the function pushes EBP. Push EBX. Okay, I'm actually unsure what that is all about. Probably some call error and callee saved registers or something like that. Maybe it's a good time to get my calling convention Wikipedia. Cause I always forget. Yeah, callee. So my guess is that EBX is a callee. Okay, I'm not finding what I thought would be there. Okay, push EBX. Also like what EBX? EBX register. Yeah. Okay. Yeah. EAX EBX makes sense, right? Good. Anyway. Going back to this thing though, don't need this anymore. So it's saying set a breakpoint on this thing. Okay. Well, it would be good practice just to do this anyway. So I'm gonna do that. So make kimu gdb, make gdb. Okay, I'll clear out this stuff. So we have it. Yeah, and now I'm trying to break on test backtrace. So I can either break with a physical address. Wait, I kind of, yeah, I know we were doing this the other time, but I kind of forgot how to break on stuff. So I just did the normal thing where I'm using the symbol, which is breaking on the virtual address. And I think that should be fine. I think last time I was trying to break and examine all this code, but it was not working because this is before the transition to jumping into high memory, which is what all these addresses are. And so the breakpoint was never getting hit because the breakpoint was on high memory, but it was still operating in low memory. So let me just continue. Yeah, that totally worked. I don't know what they're talking about. Yeah, like is this wrong? Because I just had a B command which is a virtual address, and it totally worked. But I guess I'm also using Kimu and not box, so maybe box is different. Okay, how many 32-bit words does each recursive nesting level push onto the stack, and what are those words? What does our stack look like? So I'm going to, oh, okay, nice. So, 6 init. Yeah, okay, so this makes sense. So here's our stack. This is the bottom of the stack. These are the things on like above on the stack. We're about to call test trace 5. And so we can see that the first thing on the stack is the saved program counter from the call instruction, because that's what we're seeing right here. We're doing call test backtrace. That's going to push the address of the next instruction onto the stack, which is this f blah 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 d4 thing, which is exactly what we see here, f blah 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 d4. The next thing above, so before that happens, we set the argument to the function, which moves a 5 onto the stack, and that's exactly what we see here. And what's it saying to do? Like continue again, and then we'll dump the stack again. So now this is our new bottom of the stack. And I am a little bit disoriented, actually. Wait a sec, what? Maybe I need a bit more context? Okay. So here was our original thing. Okay, I think I was totally wrong before. I think I was like saying 8 bytes or something, but I think I was totally wrong. So then, I mean, before I even do that, I just want to look at the code again, though. Oh yeah, okay, of course, because there's all these other function calls that happen. So one round. So like imagine we're before the first test backtrace call and we have a certain stack state. We execute the test backtrace call and eventually we're going to have another, man, this is so, I'm going to make another diagram just to help understand it. Okay, so pretend we are like here or something. We have 5. Why is it such a big 5? Okay, we have the 5. We have, okay, so this is the state. We execute this assembly instruction, and this is the state of our stack. There's like some other stuff up here, but it's not relevant. So this is our stack. And then we're about to call this function. And so that pushes one more thing. It pushes the D4 thing, right? It pushes this onto the stack. And then we actually get into the code here. We start doing stuff. Eventually we're going to hit the breakpoint again, but the question is, what does the state of the stack look like at that point, and what code executes in between the two that causes a difference? And before I look at the answer, which is in my GDP right now, I'm going to try to just reason that out like manually. So we called into, so we're running here right now. We already did the call, so the PC was pushed, the program counter was pushed. Now we have another function call, which passes 2 arguments. So this is going to be a pointer, and this is going to be an integer. So that's going to be 2 more things. And so let's just map that out. So we're going to pass, color this differently. So now I'll pass the x, and we'll pass the format string for the cprintf call. And then we are going to do a call of cprintf, which is going to push another PC, saved PC, and specifically it's going to be hex this. It's going to be this thing. This is the instruction after. No, wait. Yeah. This 5.5 is the instruction after the call, and so that's what we're going to see here. And what next? So we have this thing, and then we call that, and then now we execute the logic, and in this case, it's going to take this branch, and then it's going to push another argument, this x plus 1, or x minus 1. I'll make it a different color so I can see it more clearly. It's going to push the x minus 1 onto the stack. And I'm assuming it's all 32-bit things. Int, a pointer, x-1, also an int. Test backtrace, and this is the argument for test backtrace. And so here's my guess. These are all the things that are on the stack. And I think I might be wrong. I didn't remember seeing the 5 in the stack dump, but here's my best guess at what's going to be on the stack. And then here we're going to call, oh wait, no, I'm wrong. Then we're going to do the call instruction, which is going to push another thing on the stack. And in this case, it's going to be this one, 68. I should have just copied this one. Hex 68. So that's the call instruction that triggers the test backtrace. And the breakpoint is going to actually hit when the first instruction of test backtrace runs, which will be after the call instruction, because the flow will go like, it'll be like, okay, running all this stuff, call test backtrace, but then the breakpoint only actually hits on this thing. And so by the time we get to here, this instruction has already completed, and its side effects of the push under the stack have been completed. So here's my official best guess at what the stack looks like. And I kind of want to draw a symbol of like a bracket. Is there an easy way to draw a bracket? Yeah. Did that not work? It's yellow, okay. Or whatever, okay. Make it thick. And in summary, this is basically what's going to happen. So this was already on the stack before the first call of it, and then all this other stuff gets added onto the stack, and then finally we're going to hit the breakpoint. It's going to be this, and let's see what the actual answer is. Okay, here we go. 68. Yep. x-1. 4. Yep. 5. Okay. Interesting. So I don't have a 5. I'm wrong about that. Don't have a 0. I'm wrong about that. 54. Okay, I'm very wrong. How was I possibly so wrong about this? So this looks like the format string. Okay, no, never mind. I don't know what that is. What are all these 54s? What happened? Okay. Kimu already gives me a backtrace. Okay, what is going on? So this is previously I was dumping the stack, and this AAC thing was there. So this is totally unchanged. What is this? It actually looks, I mean, I don't know. Let's search for it. FF8, I don't see it as a code symbol or something. Okay. Am I like reading this wrong? Yeah, what is this thing? Okay, so how would I go about it? So what was my problem? So how do I find out? How can I explain this? If I can probably read the assembly. So to really find out, we probably just read the assembly of test backtrace and see what actually happens here. But it's time for a 20-second break, so I'll be right back. Okay. Oh, I forgot about the frame pointer. Did I? Yeah. Yeah, I totally forgot about all the frame pointers. Okay. Yep. Yep. Okay, let me try again. Okay, so that was my first try. Here's my second try. There's gonna be a bunch of frame pointers around here. So, like, conceptually, this is like, I think kind of right, but we're just missing some stuff. So definitely doing the call, and then we have a saved EIP, saved EBP, pushed onto the stack. Oh, wait, but then there's all, okay. So yeah, I was very wrong because I was also not thinking about stack variables, but there are no locals. Oh, wait, but cprintf, no, cprintf, wait, no, I'm confused. I'm actually very confused. The reason I was wrong is because all of the arguments for cprintf that get pushed should get cleaned up by the time we get to here. So I'm wrong about that, actually. So this should basically be like full, like have no effect on the stack as far as we're concerned. I think maybe, but that's a bit confusing to me. So my new theory is that, okay, we do the call instruction and then this thing starts to run. We push EBP, right? So we have the saved frame pointer. And then we push EBX, but there should also be like a pop EBX. Like, where is EBX used? Push EBX. Yeah, okay. I mean, this is that thing I didn't understand earlier, and that's affecting this a lot. There's for some reason, EBX is being pushed. Several times. Push EBP. EBX is pushed and saved, and then the hex C is subtracted to make room for the stack variables. And then, okay, it's confusing to switch back and forth between Intel and AT&T syntax. And then I think this is like the address of EBP plus 8 maybe is stored into EBX. Or is that a dereference? No. I need to ask what this does. I forget. Eight bytes above the base pointer. Which is, oh yeah, okay, that's accessing the first argument. Yeah, because EBP is set here. And in the meantime, there is a saved EBP and a PC on the stack. So basically it's like, at this point, EBP points like here, and then it needs to go up 8 bytes to access the 5, which is, it's trying to like, yeah, do that to print it out. And then it pushes that along with the format string, calls the function. Oh wait, wait, it adds 16. It adds 16? Wait, okay, let me just follow this through. So we have the saved EBP. Just gonna move this out of the way. Okay. Saved EBP, push EBX. Which is the saved EBX. Then we push the new arg, which is x, push the format string. This. Then do the call, which pushes a PC. No, but wait, but I'm going too fast. Then we add, oh wait, no, yeah, wait a sec. Push the PC with the 5.5. And then that returns, and that pops this thing off the stack. And now we're here, and now we clean up 16 bytes. We bring the stack pointer all the way back up here. No, that sounds kind of wrong. Because then that's like, because the call pushes something, but then it, on the way out of the function, it does a return and pops the stack. And this looks, am I wrong? Is it like, to me, this looks like it's adding 10 to the stack pointer. What does do? Right, adds, or 16, yeah, hex 10, 16 to the stack pointer. But why would that make sense? Because then it's cleaning up 4 pushes, including this like very critical. Oh, maybe it's, okay, I don't actually know. Oh wait a sec. There's this if thing here. So for some reason it like does that, and it checks EBX. Did I maybe miss some special use of EBX? Oops. I don't think there's any special use of EBX. I don't even see any EBX used until here. So that's okay, that's like, I don't get that. And then jump less than to 81. So it's less than less than 0 or whatever, jump otherwise, prepare for this thing. What's it doing? It's like subtracting the stack again by 12. Okay. I gotta be honest, I'm totally confused, actually. I don't understand this code very well. So somehow EAX is the argument for test backtrace. Which is just x minus 1. Okay, this means that EBX somehow contains the argument. It's like the 5 thing. Which, right. That's what's set here. And then the LEA is used to like do the subtraction by 1. Right. So EBX is set here, and then EBX is not, it's printed out here, but EBX retains that value. And then, oh yeah, we're testing the value of EBX to do this check, right? I see. Okay, I understand that. The only thing I'm just not quite getting is like all this stack stuff. Because it seems to me like, okay, we do, like, am I being, like, that's 16, right? Which is 4 words. So it looks to me like it's like cleaning up the whole stack a little bit prematurely or something like that. I mean, we could step through it. And so let's just say that's what's happening. We clean up. Can I? Oh no. Okay. Wow. So let's say we add ESP by 16 for some reason, clean up the format string, clean up the EBX, clean up the saved EBX, clean up the EBP, and then what? And then check, and then say we're going into this. Then we subtract by C, which is 12, which allocates like 3 word slots, basically. Pushes the yeah, like what's up with that? Pushes the x minus 1, and then does the call. Which has it's going to push the 68 thing. Yeah. Very non-obvious to me why it did this. Like this whole, I mean, this whole thing is weird. I don't really get why it even popped this. I'm either reading it wrong or I'm reading it right, and there's some reason why this is okay. But let's go back to this thing. 68, then the 4, and then, okay, but, okay, we see a 5, a 0, and then a 54. So 1, 2, there's 8 words in between. There's 8 things before the D4, which is not at all what I have here. So I'm missing something. Yeah, I'm being a bit stubborn by like not stepping through it and by trying to just read the assembly and then figure out what happens. But I kind of understand why there's a 5 here, I think, because that's what the x is. Yeah. Okay, let me, so we went pretty deep into that. Set a breakpoint bot, examine what happens every time it gets called. I mean, I'm just going to do this again. I'm just going to continue one more time. And dump like a ton of the stack. I think my command is right also. I mean, also interesting just to point out that it says entry to page dir, which is what I was talking about earlier, because the page directory is immediately on top of the stack, and it actually points that out in the dump. So yeah. So apparently, anyway, this is the original stack frame we were watching at, and apparently on every time in between, like between every breakpoint, 8 things get pushed onto the stack. It always ends with the 68. This is like the current argument being passed to the function. This is like the previous one for some reason. There's a bunch of these empty slots, and then there's like this kind of random pointer, which now that I'm looking at it is the saved EBP, because it's like in the stack region, which makes sense because it's the first thing that's pushed after the pushed PC. So at least, I mean, even though I don't really understand why that is, I can observe that is what's happening. Let me try that one more time. Yeah. So now we have this original one, and then we're the third deep, and every single time there are 8 words being pushed to the stack. How many does each recursive nesting level, and what are those words? And what are those words? So maybe I actually do need to understand this. Okay, I'm going to stubbornly continue to read assembly. Push. Right? Maybe the code of cprintf matters for some reason? It's kind of dumb. I feel like, how do I find the definition? Here we go. But I feel like it shouldn't matter. I feel like cprintf should not matter. The code path that we're executing in between these two is just like what we see here. Sub 12. Push, so push EBP. Push the saved EBX. Oh, wait, I see. Okay. Okay, wait a sec. Let me do this one more time. I was kind of, yeah. Let me just walk through it really step by step. I'm confident we can actually understand this. Okay. So, push saved EBP. Saved EBX. Push EBX. Sub by 12. Right? That's the thing I was missing. That is completely the thing I was missing. Because that I was looking at this hex 10 and I was like, what the F is going on? But I forgot about this thing. That is critical. Push EBX, which is the argument. Push the format string. Push the PC, but then that gets popped. Like technically push some 55 thing like I first guessed. Call cprintf, and then on the as cprintf returns, it will pop that back off. So that's not there anymore. Then what? Add hex 10, which is these 4 things. So these 4 things go away. Okay, 20-second break time. Okay. Add hex 10. So before we subtracted hex C. And so hex 10 is going to be, yeah, these 2 things. And then like partially of like what this thing was, which I don't totally understand. Test, jump to, no, don't jump. Sub by 12 again. By 3 more? Is that like what? Sub by 12. Push the new x minus 1. I don't know, man. Push the new x minus 1 and then call with the 68. Is this, man, what is going on? Is this, could this possibly be right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Yes, I think that's it. These are the 8 words that we see in the debugger. To me, it is totally mysterious what all these empty slots are that are not really used. But maybe if we look at the code, we can find. There's no local variables, really. So I don't understand why there's so much stack space reserved. But anyway, whatever. I think that's actually the answer. So we go back to here. It's like the save PC, the actual arguments, the x minus 1 thing. 4 bytes of like kind of random stuff. 1, 2, 3, 4. Then the saved EBX, which is the one from before. No. And then the saved EBP. Approximately something like that. I kind of don't get the saved EBX thing still. Yeah, I would like to understand that. Is EBX? I'm just gonna ask ChatGPT. x86. What are the caller saved registers? Or no, I think I meant Kali saved, because anyway, we'll see. Okay, stop. EBX is the first one. Often used to store data that should be preserved across function calls. I mean, I thought I was looking for that. Calling conventions. Right, x86 calling conventions. Why is... Okay. Calling convention. Oops. Man, why are there so many? I just want a simple table of like what the registers are. EBX. Why is the word EBX? This is 64-bit. Some thoughts on calling conventions. OS Dev Wiki, please. Okay. Thank you. I think this is exactly what I was looking for. Preserved registers. Or I guess I don't really know what preserved registers means. But caller saved must be preserved by the call of the function. Okay, I mean, that just explains it. That's why there's all this EBX stuff happening. And, for example, yeah, I don't know what this is, but all right, I think I have looked into this enough to be able to continue with the assignment, which is what? Mon backtrace. You may find the read EVP function useful. Display a listing of call frames in the following format. Are the first 5 arguments. If the function was, if these will not be useful, why can't the backtrace detect how many arguments there actually are? Yeah. Well, from the context of the code running, it can see where it like has this EBP chain that's like a linked list, and from there it can see like the PC, for example, which should be right above the EBP, I believe. But then it's impossible to distinguish the pushed arguments from any other stack data that the function had. Why? How could this limitation be fixed? I don't. I mean, one dumb way is like, as part of the calling convention, you could actually pass the number of arguments, maybe, but that's easy if it's just like a bunch of words, but if you're passing like structs that are larger than one word, maybe that gets complicated. Although I think the answer is just also like, as part of the calling convention, you pass just however much stack space basically was used, but that doesn't let you print out each argument. Yeah, though you need to know the separation between the different arguments. Like if they're all words, it's very easy. But if things take more than a word space, you need to know kind of how big each argument is, and that's complicated. But anyway, okay. So like, let's see if I can do this. I'm actually a little bit kind of nervous. I don't totally know. I haven't done this before, but which you should call mon backtrace. Should display in the following format. Okay. Mon backtrace, my code here. What is a trap frame? Do I need to know what a trap frame is? I kind of don't think so. The currently executing function, namely mon backtrace itself. All right. Yeah, let me see if I can do this. So also what? So I'm going to break mon backtrace to C, continue, dump ton of memory. Oh no, I didn't quite get there yet. Mon backtrace. So luckily it also takes a bunch of zeros for like, oh, because of these three things, which are not used or something. Okay. So what do we need to do? It's going to be kind of a loop through all the stack frames, and eventually the loop condition is going to end. And yeah, okay. But so we don't need this. We don't need this. I'm just going to clean this up a little bit. Okay. This is just what we need. Okay. My code here. Do we have bools in C? I don't even know. I don't think we do. Is done. Yeah. This is super messy. While is done. And then presumably we're going to be doing some stuff inside this loop for every stack frame, and there'll be some condition that we will maybe set is done to true or to 1 at some point. x86.inc read ebp. Okay. What does EVP? So basically, yeah. Just coming back here for 1 second. Or basically, okay. Yeah, so our code is running when at the, if you imagine this is mon backtrace. Cool. Let me actually find it. There's nothing here so far. But yeah, but as soon as we add some code, we will have. So we will have an EBP. Like as soon as we add literally anything here, I should done equals 1. I'm just gonna do cprintf hello. Right, okay. Just to get started with this. Make you hello. Yeah. So now so now we're here. As soon as we have literally anything, we're gonna get the function prologue. And our code, it's basically after this move. So we want to print. So we're printing our EBP. Okay. The base pointer into the stack used by that function. Position, just right, okay. Is the function, yeah, okay. So just to make a bit of progress, this is the first step. We need to call read EBP and get EBP. Uint 32 t b equals read EBP, right? And we're going to print that out. I don't really remember the. Okay, and let's just do this. Oh, but it's I need to print it in hex or something like that. So I kind of don't remember the code, but something like this. F18 is that? Okay, that I think that could be right. And all of the, yeah. So here was our mon backtrace. The stack pointer is actually going to be, it maybe should just be exactly this value or something, F1C. I don't think it should change each execution. So it's an F18, which I kind of don't get, but I'm just going to kind of keep going. So we read the EBP. And now the question is, how do we need to read the top of the stack, right? What else does it say? Okay. So how would I get the EIP? From C code. I am going to need some other things here. So I need to get the ESP. Once I have the ESP, that's, yeah, okay. I am going to, yeah, oops. I'm going to gather all my data and then print everything out. So ESP, returns, okay. I'm just thinking about what type to make this. Does this work? Can I print out a void pointer also? I kind of don't remember. So I'm just going to print out ESP and see what happens. Yeah. Oops. Okay. Maybe I should get rid of this this function call. I think that is slightly confusing things. F18, F08, is that right? That would no, it's like totally different for some reason. Okay. Whatever. It actually, I guess it didn't change. Did it change at all? I guess no. This slightly changed. Whatever. But I think that kind of makes sense because EBP somewhere, and in this code we subtract ESP hex 10 actually. Oh, hex C. Did that change? I was going to say it makes sense for there to be a hex 10 difference, but whatever. Okay, but I'm having a bit of trouble actually, because so going back to the diagram. "20-second break." Right, so we can access EBP because the register, oh, so we are accessing, wait a sec. I feel like I'm not understanding something that I should be understanding. These things are like inlined, and it's pretty much just like, it's really just assembly, right? That gets reads EBP something, reads ESP, and then we're doing some stuff there. So these functions have, these inline assembly functions really don't, they literally compile to single instructions. So that makes sense to me. The question is how do I get, so I can get ESP. Oh, I see. Okay. When you have EBP, EBP is pointing, right? This is, yeah. Okay, super basic stuff here. EBP, like have a function. EBP is always pointing to like, because you push the argument, you push the PC, you push in EBP, and then EBP, the real EBP is going to be pointing right there. So then you can always get, so from there, that's like your kind of entry point, and then you can get the old EBP, basically. So let me, I'm also gonna drag this away. I think I'm slowly getting there. Okay, so we can read the EBP. Then I'm just gonna do like, I guess I'll also just keep with the underscore convention for now, although I think I do like camel case a bit better. So old, or maybe we'll call this saved EBP, which is going to be equal to, and I think I mean, it really is an unsigned int. I mean, yeah, for the moment, uint 32t. I'm just going to do this uint 32t. Okay. That's really what EBP is. It's a pointer to a word. And I mean, all of these things kind of are EBP. A saved EBP. Also, we can also get the PC pretty easily, right? That's going to be EBP plus 1 dereference. What is this? Okay. Right. It's EBP is the uint32t plus 1 and dereference that. Okay. And then we're just gonna be printing stuff out. So I think the ESP was a bit of red herring. All these things are pointers now. Saved PC. Right, okay. Does this work? Oh, what? Okay, so interesting that I need to be constantly casting. Yeah, that's like something to clean up later once I figure out how to actually kind of do this. Oh, I could technically do this. I could make this a double pointer. Wait a second. No, I mean, it's wrong to declare the PC as a pointer to uint32t because it's like not. Yeah, what am I doing? Yeah. I think I'm making this too complicated. I'm just gonna do this for now. I mean, it is true that EBP points to uint32. That is actually right. It's not true that PC points to uint32, but that doesn't matter for immediately right now. Right. Saved EVP. You know, it would probably be a good idea to debug this to kind of confirm some of these things. Oh, continue. Okay. Now let's do our big stack dump. And what did it say? Oh. Interesting. Okay, because I haven't run the code yet I need to like step like a couple more instructions. I think that was actually all I needed to do. Yeah. Maybe? Let's do a fresh dump. Did that change? Yes, it did. One more thing got added. Yeah, okay, now that was actually important to do, which is making more sense. So in the actual code execution, it's saying the literal current status of EVP is the 18 thing. The saved one points higher in memory by hex 20. It seems like the PC is this thing. Is that what we see here? Yeah, exactly. So we have, our thing at 18, the pushed EVP is 38, the saved this thing is hex F, 8F, and then what did it say to do? Print out 5 arguments, 1, 2, 3, 4, 5. Okay. Then is less than 5. And then so what's the actual thing to do there? We just need to keep reading past yeah, so uint 32 t arg equals, so then we have our, so EBP plus what, 2, I think? Oops. 0. So EBP pointing here plus 1 plus 2 gets to the start of the arguments plus I. Okay. And then right, arg. This is just going to be like a hex this thing, I think. something like that. How do I, yes. Okay. That was a total guess. I want it to print, okay. Print. Zero x8. That's the thing. And just out of curiosity, and okay, I guess I'm comparing it against the old backtrace, which I'm not sure is right. But I guess so. Yeah, I think that is 0, 1, 2, 4 zeros, and then the D7. Yep. Okay, let's keep it moving. I think I can maybe even finish something close to this by the end of the stream. Okay, what was it? EVP, EIP, 5 args, and that's it. So I'm basically done. I just need to figure out how to end this. And the ending is when, I think it's when EVP equals 0. Because at the very top of this chain, like in the entry.s code, we started off with nuking EVP, and then this thing pushes it onto the stack. So let's pretend we're on the first, stack frame. And it's like, okay, EVP is something valid. Then the saved EVP is going to be 0. So if so in the first stack frame, EVP is something. EVP is like some valid thing. The pushed thing though is going to be a 0. We're going to read a 0. So this would be like a null pointer basically. Call this a null. That means we are done. There's nowhere. But wait, okay, this is like obviously wrong to be reading the current EVP every time. So that needs to come out. And so it's gonna be something more like, okay, we have a current EVP value. While EVP, yeah. And then something like, was saved EVP, and then we recurse up. So in the first stack frame, so we kick things off by reading our current EBP, right? We get a bunch of information based on that, like the saved EBP and the PC. We print out everything we can, and then now it's time. Like it's not like I think I said recurse just now. It's not right. It's just we keep going. Then we kind of reset, point EBP back to the new one. Yeah, I think it should be something like this. And eventually the saved EBP is going to be null. And that gets saved into EBP, which gets detected. Okay, let me try this out. Hopefully, it would be cool if it did something. I mean, it didn't crash. It didn't infinite loop, so that's a good sign. And indeed, saved EBP is 0. Going into GDB just to do a double check. Yeah, make GDB bmon backtrace. I'm actually going to print the test backtrace a couple times. And then I will just to kind of see what a sense of what I would expect to see. So all this expected stuff. I mean, actually, can I just immediately? Yeah, I mean, this kind of looks right. A bunch of 68s and the D4 frame with the 5, 4, 3, 2, 1, 0, AAC. And this is like the first. This is the frame of test backtrace, because like the arg is there and the saved PC points. Yeah. And then this is the stack frame for x86 init, which this is all bogus, I think. The key thing saved, let's check this out. E3, that should be totally visible. No, it's going to be in entry, and it should be like right after the call. So with the call, yeah, call this thing, and then the saved PC is 3E. So that's exactly what we see here, 3E. I feel like, I think I did it, actually. I think I did it. I mean, I think I kind of did it on the first try a little bit too, which I'm pretty stoked about. Yeah. Didn't crash, didn't infinite loop. Pretty sure that's correct. Doesn't conform. I came in just now on it would be cool if it did something. What a mood. What a mood indeed. Thanks, Kat. Yeah, I mean, I think you actually tuned in to one of the best moments in my entire like 15 weeks of doing this, because this is the first week where I actually have written a somewhat like decent amount of code. Actually, I really haven't done that before. And yeah, I printed out the stack trace on the first try. The code's junk. The code's garbage. I don't like this code. Like, there's so many things bad with it. Like, I don't think this type is really the right type. Ideally, there would be a better way to express it without all this mutation, maybe, but that also kind of comes with the territory. of doing the iterative algorithm. But otherwise, I think it kind of worked. So it's good timing. I need to end the stream now because it's 6. But let's just check in and see how we're doing with that class assignment. I mean, so I just did this one. And now it's talking about what's next is like actually using some debug info to print out function names, which is like hardcore. Emotional roller coaster of the most code you've ever written, but also oof, it's bad. Lol. Yeah, I mean, I'm not. Yeah, thanks. I mean, I'm overjoyed actually. I mean, the hard part is writing the code. Cleaning it up and making it better is the easy part. But the hard part is actually kind of writing the code. So, cool. This looks pretty hardcore. I don't even know if I can even do this because in order to get my kernel building, I needed to disable stabs. I like removed the G stabs because it wouldn't build otherwise. So I don't know if I can continue with that specific assignment, but that's cool. All right. I am going to end the stream now. Let me just plug myself. I have a Discord if you want to join the Discord. It's linked in the description of this video, but I'll also just post it here for anybody watching. Oh man, my 20-second break timer just fired off. I'm just gonna kill it. Okay. I'm gonna copy my Discord. Thank you, Kat. Yeah, please, like, comment, subscribe if you are interested in the stuff I'm up to. I'm here every week just trying to learn how to be an operating systems programmer. So thanks a lot, and I will see you next week. Peace.